Okay, hello to everyone. It's very nice to see you all. Today, we're very happy to have Ioannis Tsiares, who is going to tell us about Conformal Bootstrap Universality. So Ioannis, take it away.
Great. Thank you very much for the opportunity to speak. It's a great pleasure to be speaking at this group. So yeah, I'm going to be telling you about some work in progress in collaboration with Sylvain Ribault in Saclay. This work is going to come out hopefully soon. And my talk is also going to be based on some previous work of mine in collaboration with Scott Collier at Princeton, Alex Maloney at McGill, Henry Maxwell, who is now at Stanford, and also to Kirano Masao, who's at the University of Tokyo. So as an introduction, of course, as we all know, conformal field theories constitute a very special class of QFTs, which on top of the Poincare symmetry, they possess the so-called conformal symmetry. And these theories are important in theoretical physics because they describe the plethora of phenomena from fixed points of RG flow to universality of different systems of criticality, and of course, quantum gravity in ADS through the AD-CFT correspondence. Now, in two-dimensional CFTs are a bit special compared to their higher dimensional cousins. In part, one can say because of the existence of an infinite number of conserved charges. So these theories are very ubiquitous actually in both physics and the math literature. So one finds application, of course, from the usual 2D condensed matter system and world system theory, but also one finds novel applications to topics like number theory, random matrix theory, quantum groups, and so on. So we would like to delve into this kind of theories today and understand a little bit their structure. And let me say right from the beginning, please feel free to interrupt at any point. I hope I can hear you all and ask questions if you like. Okay. So I'm going to be interested today in Euclidean correlation functions of local operators on various Riemann surfaces. So in particular, I have in mind something like this, which is supposed to be a cartoon of a 4-point function of 4 primary operators. Here, I'm imagining that I have an operator at the center of the circle, and I can have a 4-point function on the sphere, or let's say a 2-point function on the torus like this, and then any higher genus endpoint function. And of course, we know that using the power of the operator product expansion, which is true in any CFT, not only in 2 dimensions, I can calculate all these correlation functions basically by a list of the so-called CFT data, which in 2 dimensions at central charge C, they consist basically of 2 types. One is the dynamic, which is basically a list of primary operators OI, along with their scaling dimensions delta and their spins, and also their OP coefficients, Cij, and also the so-called kinematic data, which I have called here collectively conformal blocks, and they are supposed to capture the contribution from the so-called descendants of the primary operators OY. And here by conformal blocks, I mean any conformal blocks in any Riemann surface like this. So the question that we like to ask today is how the CFT data constrains from consistency conditions. This is the conformal bootstrap philosophy, basically. And we would like to ask, especially, if we can find any universal features of this data. And moreover, we can try to do that analytically as much as we can. So if I am to draw a very, very modest cartoon of the space of theories that the bootstrap has taught us so far in 2 dimensions, I will draw maybe something like this. So every dot here is supposed to represent a particular theory, a 2D CFT, in the complex central charge plane. And you see here, since I'm exploring the whole complex plane in the central charge, I'm not interested necessarily in unitarity. So I'm just classifying here theories in terms of crossing, if you like. And you see that, for example, we have a lot of theories here on the line from -infinity to 1. We have, for example, the minimal models and PQ, the non-unitary ones, and of course, the unitary ones. We have some systems describing condensed matter system, let's say here, Q-state Potts model and Owen theories and so on. We have the compactified free boson. But you see that actually in a regime that is of large and positive central charge, we're actually lacking a working example of a 2D CFT. And again, here I'm being very, very modest. I'm not including WGW models, nonlinear sigma models, so on, or super conformal field theories, etc. I'm just interested about 2D CFTs, let's say, that have no extended chiral algebra, they're just Virasoro, and they are non-holomorphic. So the point of this is to basically illustrate that we have a handful of theories for C less than 1, but not so much is known for C, let's say, bigger than 25. Of course, we know that Liouville theory is one of these examples, and this is going to be crucial as we're going to discuss later. But in general, we don't have any example more than that. So the general question that we can try to ask is, like, is there some structure of the bootstrap in the complex C plane? Is there some kind of relations that we can make? We see that there is all these bunch of theories here in this line, but nothing here. Could we ask maybe if there is some structure of the conformal bootstrap as a function of C being complex? So, question?
Yeah, can you just remind me the basic reason why there's nothing between 1 and 25?
Right. Actually, there are many rational CFTs with these kind of simple charts here. Again, I'm restricting myself to just Virasoro CFTs with no extended chiral algebra, just pure 2D CFTs with, let's say, no WZW models and so on. And of course, Liouville theory can be extended down to the regime of central charge equals 1, but it's a little bit subtle. I can say maybe that the rigorous construction of Liouville theory right now, people understand as making sense for C greater than 25. That's all. But
yeah, I'm just wondering, I forget this. I think I knew it at some point. Why 1 and 25 are special numbers?
Right. We're gonna see in a bit why.
Okay.
So I'm gonna try to explain. Please feel free to ask again if this is not clear.
All right.
Yeah, that's a good point. So I'm going to try to approach this second question that I have here. And basically, the first goal of my talk, so I have two goals for this talk. The first is to understand an important bootstrap tool, which goes by the name the Crossing Kernel in 2D CFTs. And this is basically an object that implements changes of basis transformations. So if I have a conformal block here in some frame 1, I can write it as a linear combination of conformal blocks in the frame 2, let's say, with a kernel that defines exactly what I mean by crossing kernel. So this kernel has here two indices that takes care of these two indices of the blocks here, and in principle, it's a function of the central charge. So we will try to understand this object today as a function of the complex central charge. Now, it turns out that if the central charge is in the region of the whole complex plane, except the line from -infinity to 1, so in my previous graph, everywhere except this line, this expression for this kernel, at least for the case of the 4-point function on the sphere, as we're going to see later, was provided by Ponceau and Tessner in 2000. So these are two mathematicians which made heroic work and actually construct this crossing kernel here in the case of the 4-point functions explicitly. So they found it as a function of the internal momenta, which I call here P and P prime. The notation is going to make sense in a little bit, and as a function of the central charge. But crucially, their expressions, they make sense only in this region of the central charge. Now, what about the complement region, the line from -infinity to 1? It turns out that to date, as far as we know, no expression for this kernel exists. And in principle, we expect that this object is a kinematic object. It implements transformation between kinematic objects, namely the conformal blocks. So it should be there in principle for this regime, based, if you like, in Virasoro representation theory. So what I'm going to show today is that we're going to be able to write down an expression for the kernel exactly in that regime. And we're going to discover that actually this kernel takes a very interesting structure, which consists of basically a meromorphic function, a non-meromorphic function, times the kernel of Ponceau and Tessner, this math PBK, if you like, except evaluated at rotated values of this P variable, which again, it's going to make sense soon, and crucially evaluated not at C, but at 26 minus C. So we're going to discover that the kernel in this complement regime takes this very interesting form. And in particular, we're going to see that this includes and actually generalizes the already known expression that we have, for example, for minimal models. This is, if you like, an analytic continuation for any central charge in this line. So this is the first goal of my talk. And then in the second part of my talk, I will try to apply this to learn something about the bootstrap. So in particular, we're going to see that we're going to be able to analytically prove crossing symmetry for something that I guess more or less you are familiar with, I suppose, something that's called the Timelike Liouville theory. And crucially, this will be proven upon the fact that space-like Liouville theory is cross-symmetric. So we're going to be able to use the information that space-like Liouville satisfies crossing and modular covariance to prove that also time-like Liouville theory is again cross-symmetric and modular covariant. And this expression for the kernel, it will be important for that, as we will see. Now, more ambitiously, we will try to initiate, if you like, a program of like universal conformal bootstrap connections between theories or maybe bootstrap solutions for theories with C less than 1 and theories with C greater than 25 in 2D CFTs. And this 1 and 25 here is exactly motivated by this relation that we find here. So here, again, as I was saying before, this kernel at central charge C is related with a Poisson testing kernel at 26 minus C. I'm gonna elaborate more on that, of course, but I just want to motivate a little bit also with the question asked, this 1 and 25. And in general, like we will try to get a glimpse into the structure of conformal blocks, let's say, for these different regimes of central charge, and also try to say something about connection between large positive and negative central charge. I won't have anything very concrete to say about this at this moment, but these are the questions that we have in mind in general. So this was my introduction. Are there any questions so far? Okay, yes, I will continue. Please feel free to interrupt again. So this is the outline of my talk. I'm going to start with a 2D CFT primer just to make sure that everyone is on the same page. And then I will describe explicitly what we mean by crossing symmetry and modular covariance in 2D. Then I will introduce these crossing kernels, and I will explain a little bit the structure. And after that, I will try to address my first goal, which is try to construct these kernels now for this complement region of the central charge. And also my second goal to discuss this conformal bootstrap application given this expression for the crossing kernel. And I will end with some summary and future directions. Okay, so some very basic facts that I'm sure you guys are familiar with. So again, contrary to the higher dimensional CFTs, in 2 dimensions are a bit special because of the existence of the infinite dimensional algebra of symmetry, which is the Virasoro algebra. And I have written it here in terms of the modes of the stress tensor, LM and LM bar, and C here is the central charge. So once we have the symmetry algebra, then the next thing that we want to do is to construct the reducible representations of this algebra. And here, these are labeled by 2 conformal dimensions, of course, H and H bar. And we have an associated highest weight primary state, H, which is defined as eigenstate of L0 and also alienated by all the modes with n positive. And then on top of that highest weight state, we build the so-called highest weight module, which consists of all the descendants of the primary. And these are constructed like so, acting with the raising operators of negative integers here. And sticking to my notation, I'm going to call the scaling dimension delta, which is plus H and H bar, and my spin H minus H bar. And here I have the twist, although we're not going to need it too much. And then the Hilbert space of states, my theory consists basically of the direct sum of the tensor product of the holomorphic and the anti-holomorphic highest weight module of H and H bar. Okay. So of course, in any CFT, we have the state operator correspondence, which means that in any primary state I on the circle, we can associate a primary operator O at the center. So everything that I said before, I can rephrase it in terms of the primary operators, not just states. And then we have the powerful algebraic protostructure, which is the OPE, and basically tells us that at finite radius, we can expand any product of 2 primary operators as a linear combination of other local operators, namely primaries and their descendants. And these CIJKs are, of course, the OPE coefficients, which are the dynamic data of the theory, as we said in the beginning. Now, of course, we can use that to constrain the 2-point function and 3-point function in the usual way. And any higher point function can be readily constructed by successively applying those OPEs and then reducing it just to a bunch of OPE coefficients and blocks, as we'll see. Okay, so this was a quick reminder. Let me now just jump into the crossing symmetry and modular covariance. Now, just a one-to notation. So, as I said in the beginning, we will be interested in kinematic quantities, namely those crossing kernels or transformations between the blocks, as functions of the central charge with C being complex. So, in particular, as we said, this includes both unitary and non-unitary theories. So, theories with set less than 0. And we're going to adopt this particular parameterization of the central charge, which is basically inspired by Liouville theory, if you're familiar with it. So I'm going to trade this C parameter with the B, which are related in this way. And you can think of B as roughly the square root of the central charge here. In particular, the first regime that we discussed, namely the whole complex plane except the line from -infinity to 1, this is captured by B being complex with real part positive, whereas the line from -infinity to 1 is captured by B purely imaginary. And sometimes I will denote B with -I veta, where veta here is real, and I will denote the central charge like so. On top of that, we're going to parameterize also the conformal dimensions in a way, again, inspired by Liouville theory. So instead of H and H bar, I'm going to use mostly the momenta P and P bar, which is related in this way. And Q here is the B plus B inverse. Okay. So let's consider a general correlation function of n local operators in some genus G Riemann surface. So as we said before, after successively applying those OPE between the operators, the amplitude is basically reduced into a product of elementary Legos. We can have a pictorial picture of this OPE reduction of the correlation function by using these pairs of punts, which are supposed to represent the OPE coefficients between three primary operators. So for example, if I am to compute a two-point function on the torus, I know that whatever this correlation function is, it for sure will have the structure of a product of two OPE coefficients times whatever blocks are characterizing this surface. Exactly because this surface is made out of two pairs of punts, two Legos, two elementary Legos. Similarly, a genus 2 Riemann surface is again some expansion that includes some conformal blocks, but crucially, the dynamical data just involves a product of two OPE coefficients, exactly because this surface is made out of two pairs of punts like this. And now, showing the surface in different ways basically leads to equivalent description of the correlation function. This is exactly the conformal bootstrap in the Euclidean sense in 2 dimensions. And of course, this is a manifestation of locality. So we know, of course, the two canonical examples of this, which we can phrase in this language. So the crossing symmetry of 4-point function of the sphere, we can either take the S-channel OPE, let's say we have pairwise identical operators here. We can take the S-channel OPE and we have an expansion like this, which can be depicted as showing the surface by pairing these Legos in that way. Or we can take a T-channel OPE, and then again, we can have some OPE coefficients times the blocks, which can be thought of as pairing the Legos on the T-channel. Notice that the dynamical data, they are different in these two expansions, but again, I have two of those because I have two elementary Legos making the surface, basically. Now, another elementary example is the modular covariance of the torus 1-point function. So in the case of the torus 1-point function, I have one elementary Lego, so my expansion takes this form. I have one OPE coefficient, and then the so-called torus 1-point blocks. And by applying the S transformation on tau, where tau is the complex parameter of the torus, tau going to -1 over tau, then I get an equivalent description of the same 1-point function, and the crossing relation, if you like, takes this form. So we don't just have an operator and the correlation function being equal to the original one. There is this covariant factor here that basically indicates that this is a primary operator. But this is the modular covariant crossing equation, if you like, in this case. Now, of course, if we take the special case where the external operator is the identity, then this reduces to the familiar modular invariance of the partition function, where this OPE coefficient, basically in the proper normalization, they become the degeneracies of the states running on the circle, and these blocks here reduce to the so-called characters of the partition function. Now, there is a very powerful result due to Moore and Seiberg in '88, which basically tells us that if we are handed a 2D CFT and we check crossing symmetry of all of its 4-point functions, as well as the modular covariance of all of its torus 1-point functions, then this is sufficient to imply that all the higher point functions and higher general point functions, they are crossing symmetric and also modular covariant. So this is a very powerful result, which actually tells us that the crossing, the 4-point crossing and the torus modular covariance are the elementary, if you like, building blocks of crossing symmetry into the CFT. And this gets me to the next topic of introducing the crossing kernels now. So we saw the statement of crossing symmetry in the case of the 4-point functions on the sphere. So we had some expansion on the S channel equal to an expansion on the T channel. Now, it turns out that it's a trivial fact of life, which is actually an exercise in the Moore-Seiberg lectures in '89, which is pretty fun and actually, I think, introduces the notion of the crossing kernel in a natural way. So let's say we have 4 sets of linearly independent and analytic functions, fi, gi, hi, ki, where I runs from 1 to n or m. Then if these functions are such that they are related with a relation like this, then necessarily one can show pretty easily that capital N should be equal to capital M, if you like the cardinality of this sum. And also that F with H and G with K, they should relate it linearly with some invertible matrix. So this H here is the matrix that is to relate in this way, these functions. And this is exactly the thing, how we should think about the crossing equation that I introduced here. So the blocks in the S channel, in the T channel, they should be related linearly on the common domain of analyticity via some invertible matrix, or if you want, via a crossing kernel. So to make this even more clear, very schematically, so let's say I have some 4-point function, and this has some expansions of some OPE data, which I collectively call CI here, with conformal blocks on the S channel. This is equivalently written with some CFT data on some other channel, C tilde, times the block on the other channel. And then the blocks should be related linearly with some transformation, which is captured by the crossing kernel, Fij here. And this is a general lesson which was actually proven rigorously in the early Friedan-Schenker and Moore-Seiberg papers. They basically made concrete that the conformal blocks expansion in a specific channel is basically equivalent to an expansion in a specific basis. And different bases, they should be related linearly with some kernel that implements this transformation, the crossing kernel. And in fact, they also made rigorous the fact that we described with pictures that the sum over a complete set of states is basically showing a pair of funds and hence having all these consistency conditions that illustrate the bootstrap in this case. So here, when I draw a circle, I'm imagining I'm summing over states on the circle. This is what I mean by showing the surface. So what are those kernels in 2D CFTs? Now, as we said in the introduction, amazingly for central charge regimes in the whole complex plane, except the line from -infinity to 1, Ponceau and Tessner in the early 2000s, they managed to write down closed form expression for the torus 1-point kernel and the sphere 4-point kernel. So to make this precise, what I mean by torus 1-point kernel and sphere 4-point kernel, for the torus case, I write again the expression that I had before, and the kernel is defined as implementing transformations between blocks, 1-point blocks at -1 over tau and blocks at the original channel, tau, with this covariant factor here that implements the modular covariance that we saw before. And also for the sphere 4-point kernel, the kernel is defined as implementing just transformation as branching T-channel blocks into a linear combination of S-channel blocks. So these two kernels, they have 2 indices, the 2 internal dimensions, and also the external dimensions in each case. Here just 1, here just the 4 external operators. Now, just to flash an expression, of course, I don't expect you to memorize this or anything, but just to show you how explicit these expressions are, here is the expression that Tessner wrote down in 2003 for the torus 1-point kernel. This expression consists of some meromorphic functions times an integral. And these special functions here as b or gamma b, basically just gamma b, is the so-called B-deformed gamma function. It's nothing very complicated. It can be thought of just a generalization of the usual gamma function, except now the poles, they are not on all the negative integers. The poles are graded by this b parameter that we saw before. So the poles that are minus mb minus nb minus 1 for positive n and m and no zeros. So this is just some special function. And similarly, the fusion kernel, it has, again, a similar structure. There's a prefactor that I didn't bother to write down because it's a little bit huge. But again, it consists of all these B-deformed gamma functions. And then again, there is an integral of this, what I call SB, which is a ratio of gamma b's. That's what I call SB. So one comment that I would like to make right from the beginning is quite remarkable that these expressions are known explicitly, whereas the Virasoro blocks themselves, both for the case of the sphere of point functions and for the torus one-point functions, are not. So this is pretty remarkable. So at least something we can approach some problems, at least with this kind of expression, even though they look cumbersome, at least we have something in hand, even though we don't have the blocks. And actually, one can show that once these two kernels are known, one can ask what are the kernels in any higher point or higher general Riemann surface. And these kernels, as it was actually shown also in the original works by Moore and Seiberg, they are appropriate convolutions of these two elementary kernels. So basically, we're going to be focused on these two since they are the so-called elementary ones in the sense that I just described. So in great generality, these kernels satisfy the Moore-Seiberg consistency conditions, which were originally wrote down for rational CFTs, but Ponceau and Tension actually, they calculated, not only they calculated these kernels, but they went ahead and verified that these kernels, they satisfy the so-called pentagon identities, hexagon identities, and all these consistency conditions that Moore and Seiberg wrote down originally for our CFTs. Now, it turns out that the last couple of years, these kernels, they have found interesting applications in the bootstrap problem into the CFTs. In particular, of course, I'm omitting many things, but I'm just highlighting in the last 5 years, let's say, some advances. So in this paper, people were able to use these kernels to actually illustrate the Lightning bootstrap and the existence of these double twist Redze trajectories at large spin in 2D CFTs, which was a hard problem originally because 2D CFTs are a little bit special in the Lightning limit because they have all these tower of operators with zero twists. So we couldn't follow the usual Lightning bootstrap approach that we're following for high dimensional CFTs. Nevertheless, it looks like the knowledge of this kernel was able to capture exactly these double twist Redze trajectories as explained in these papers. In 2019 and then later, we were able actually to use these kernels to derive asymptotic formulae for OPE coefficients in the so-called Carty limit, and which was crucially at finite central charge. So what we saw is that these kernels, they can actually be thought of in some particular kinematic regimes. They can be thought of as OPE spectral densities. And by studying their asymptotics at large dimensions and finite central charge, one is able to write down asymptotic formulas for OPE coefficients, just like one writes down formulas for the asymptotic density of states, let's say the famous Carty formula, but now for OPE coefficients. And we're able to do that in various surfaces like orientable, non-orientable, and also surfaces with boundary and so on. And even more recently, these kernels, and actually the results maybe of this paper, these papers, they were able to illustrate for the first time, I guess, the essence of an ensemble average in this whole story of ensemble averages and holography in ADCFT. These authors here, they were able to write down a concrete ensemble of large C2D CFTs that capture in a nice way some very nice semi-classical 3D gravity answers. So there is a bunch of advances starting from these kernels, and we would like to understand them even more. So that's the motivation here. Are there any questions? Okay, I guess I will proceed. Okay, so having said that, let's try to move to these kernels for this region C less than 1. So what about this complement region, this region from -infinity to 1? One might ask, okay, why don't we take the Poisson-Tessner formulas, which we know as functions of the central charge, and just analytically continue them into that regime? And the answer is an emphatic no, because the special function that I described before, it has a natural boundary of analyticity exactly at imaginary B. And remember, this imaginary B is exactly this region of the central charge here. So what do we do? On the other hand, like we know that there are minimal models in this regime, and of course, for special values of beta, we know that these kernels exist. They are finite dimensional matrices that we study, for example, in the usual yellow book of 2D CFT by Di Francesco, Senecal, and Mathieu, and so on. So there should be a solution there. And also, as I was saying in the beginning, this object is purely a kinematical object. So it's based upon the Virasoro representation theory. So it should exist in general for all the values of the central charge. Now, the pentagon identities that I mentioned before, and I will specify them a little bit more, I will elaborate on them a little bit more later. So it turns out that once specified into degenerate dimensions, they provide difference equations for this kernel. So the pentagon identities are of this form. So these are polynomial equations that involve these fusion kernels. In particular, this is the famous pentagon identity, which arises from two equivalent ways of describing the 5-point function of the sphere. So just by considering these different moves that lead to the same results, one is able to write down a polynomial equation that includes only these matrices. So at this stage, these pentagon identities, they are polynomial equations. However, they have some free parameters. So in particular, the external dimensions here are some free parameters. And once I specify them into some degenerate dimensions, in particular, conformal dimensions that have degenerate representations, null states, these equations, they intend difference equations that in principle determine the kernels for any B being complex. And essentially, if you go back to the papers by Poisson and Tessner, the way they derive this expression was by explicitly solve these difference equations in this central charge regime that they are valid. So the Poisson-Tessner expression are just a special class of solutions of these difference equations which originate from the polynomial pentagon identities. And also, just to mention for completeness, there is this pentagon identity that involves just the fusion matrices, but there is a similar one that involves the modular, the Taurus one-point function kernel, the modular kernel. And this arises basically from a similar condition like this one, except in the Taurus two-point function. Now, what we did with Sylvain is basically went ahead and ambitiously solved these equations and provided a new solution in this exactly complement central charge regime. So the Poisson-Tessner expression is one particular solution of these difference equations that is valid on this central charge regime. There is another solution that is valid exactly when B is imaginary. So we solved them.
Yeah, Yanni, can I ask something here?
Yeah.
So is your new solution also valid outside of this regime or only in this regime?
This is valid only on this regime. And okay, there is a very good reason for that, is because, well, okay, let me say the following. So we find a unique solution in this regime, which takes exactly this form that I'm showing here. So let me try to elaborate. So remember in the introduction, I said that the structure of these kernels, they involve a meromorphic function, which is in this parenthesis here, times the crossing kernel of Poisson and Tessner, except evaluated not on the momenta P prime and P, but on these rotated values, as well as the rotated value of B. Similarly, for the fusion kernel, we have the same structure. And notice that this meromorphic function here, it depends on Timelike Liouville structure constants. In particular, this P and P prime are the usual momenta. This BTL is the two-point structure constant of Timelike Liouville theory. And this CT DOZZ is the Timelike DOZZ formula. So just to get back to your question, Pano, if I substitute here in this expression b equals minus I beta, where beta is real, then for beta real, these solutions are unique up to a total function of b for real beta. Something similar happens if you take b to be real. So in particular, the Poisson-Tessner expression for b real is unique up to an overall p independent factor. So it can be a function of the central charge, let's say, but not on p. But now if I consider complex b, there are more than one solutions to these equations. And the reason for that is that, so all these special functions that I discussed, like the B-deformed gamma function, so their pole structure is spanned by a grid in B and B inverse. Now, if I have to write down a solution to this difference equation for complex B, then actually any periodic function of P and P prime in this B parameter will also be another solution. But once I specify B to be either purely imaginary or be real, then I don't have a grid anymore. B and B inverse are just either all real or all imaginary. And the solution becomes unique. So this was explained also in the original Poisson-Tessner papers. Does that answer your question? Sorry, I may have said.
Yes. Just one follow-up. So for general complex B, I guess you could have some elliptic function solution.
Yeah, exactly.
General. Yeah. Right. Okay.
Yeah, I can multiply this Poisson-Tessner, let's say, expression times an elliptic function in P. Yeah, so these solutions are also valid for complex B, except they are not unique.
Ioannis, can you fix the leading ambiguity by comparing to the minimal models?
What can I fix the leading ambiguity?
So there, you said that this solution is ambiguous up to some leading function.
That's right.
But you know the answer that you should get for the minimal models exactly, and those expressions are not ambiguous.
That's a very good point, and actually that's how we fix the fact that the coefficient here is 1.
Okay.
So, and we don't have any dependence, let's say, on the central charge or any other numerical factor. Indeed, that's what we did, and that's the first thing we checked.
Okay.
Yeah. So these are the solutions that we find to these difference equations. And as I said before, and as was pointed out by Arjun, like these kernels actually, they reproduce all the known Millman model expression we checked on the Ising model and all the MP, Q, most of the MP, Q. And in particular, these solutions provide a natural analytic continuation of the known kernels in this central charge regime. Now, notice, as I said also in the introduction, that B to IB, this structure that these kernels have here, when translated back to the original central charge, is C going to 26 minus C. So in this sense, maybe I'm getting back to the original question, it looks like central charge 1 and central charge 25, they are somehow on the edge of this particular parameterization that we chose for the central charge. So if I may go back, well, do I want to go back? Well, if you remember, the parameterization that they have for the central charge is 1 plus 6 times B plus B inverse all squared. One can ask, what are the different B's that give the same central charge? In other words, what is the fundamental domain of this parameterization? And one notices that this parameterization is basically the first two quadrants for positive imaginary B. And B equals 1 and B equals I, which correspond to c equals 25 and c equals 1 are exactly at the edge, if you like, of this semicircle. Okay, so.
Ioannis,
Mhm.
so you said it's a natural continuation. Is it natural because it has some bounded growth property along the b-axis?
That's a good point.
There's this theorem that we sometimes use to show that the continuation of the Remy entropy is natural, and that relies on having a bounded growth along the imaginary axis.
I don't imply anything like that here. Maybe natural is not the best choice of words here. All I mean is that
here you mean continuation from the minimal model values,
exactly,
right? But those are a discrete set of points. Usually continuation from a discrete set is not unique.
I see. All I mean here by natural is that once you specify these expressions to the minimal model values, then right, you recover the known expressions. And then I rely on the fact that these difference equations, they have a unique solution for imaginary B, unique up to this overall function of the central charge, to say that.
Okay, so it's natural. It's natural in the sense that other continuations from the minimal models will not satisfy the pentagon identity.
Exactly.
Okay,
Yes. Yeah. That's right. So just to remind you, like right here, we're dealing with a kinematic object, namely a crossing kernel that implements transformation between blocks, which are kinematical objects. Nevertheless, we see some relation between large and small central charge. This c to 26 minus c that relates very large central charge with very small central charge, right? So at least at this level of the kinematic quantities, we are able to say something about our very first question that I posed in the introduction, which is there some structure of the bootstrap in this complex C-plane? To this level, at least at this level of the kinematic quantities, we see there is some kind of structure. And we will see a particular example where this will be important. And let me say that the appearance of this time-like Liouville theory quantities that we find in this meromorphic function overall factor, if you like, it's actually very interesting and will be proved very useful, as I will describe next. So I didn't bother to write down the explicit expression for this time-like VOCC formulas or this two-point structure constant, but these are basically depend on these epsilon functions, or if you like, the gamma B functions that we saw also in the expression for the kernels. So same special functions and then also in this time-like VOCC formulas. Okay, so let me now move to the applications. So the first thing that I would like to describe, and the first thing that I guess we are mostly more confident talking about from this work, is something about time-like Liouville theory. So time-like Liouville theory is this cousin of space-like Liouville theory, which is relevant in string theory and also in these cosmological setups. And usually this is believed to be a 2D CFT with large and imaginary central charge. So it's a non-unitary version of a CFT. And it is long believed that this theory is a bona fide to the CFT, in particular, like its correlation functions, they satisfy the usual conformal word identities and so on. But so far, to date, it's lacking a proof of the fact that this theory is, for example, crossing symmetric or modular covariant. There was an important work that I would like to mention here, which was by Sylvain Ribault and Raoul Santachiara in 2018, where they basically verified numerically that time-like Liouville theory with these structure constants here is crossing symmetric with support of the space-like theory. Namely, if you assume that time-like Liouville theory has again the same support as the space-like theory, then the correlation functions are crossing symmetric. So they were able to verify that numerically. Now, what we're going to do here is we're going to implement these kernels to prove this analytically. So I would like to sketch how the proof works. It's very easy actually once you have this expression for the kernels. And the logic is as follows. So it turns out that for a theory with only scalar primaries, so let's say some diagonal theory, the modular covariance equations that we saw in the very beginning for the torus one-point function, by using these kernels, can be reduced just in this equation. So I have a bunch of OPE coefficients, which I normalize with a two-point function. And then I have this relation between my OPE coefficients and the modular kernel. It's not very hard to show that the modular covariant equation essentially boils down to that for a diagonal theory. If you like, there is an analog of that for the Aries series minimal models, actually. So this is the crossing, this is the modular covariant crossing, the modular covariant equation for a scalar theory. And it turns out that for space like Liouville theory, whereas we know that the OPE coefficients are captured by the DOCC formula, and this B, the two-point function normalization, is the Liouville reflection coefficient. Once I substitute this here in this equation, it's trivial to verify that this equation is true. Actually, it's a particular instance of the pentagon identity because the DOCC formula can be realized as a particular element of the fusion kernel. So all that to say that indeed space like Liouville theory satisfies this equation in a straightforward manner. Now, what about Timelike Liouville theory? As I said before, this theory is defined for C less than 1, so we better use the expression that we obtained for the kernels. So the question that we like to ask is now this equation correct, where I basically substitute the OPE coefficients with the Timelike DOCC OPE coefficients, the structure constant with the Timelike two-point function, and now in place of the kernels, we have the kernels in this complement regime. So is such an equation true? And voila, it turns out that one can verify that this is exactly true. And the proof implements the fact that space like DOCC satisfies the equation. So the way the proof works is that we use this structure of the kernels. You see, here this kernel involves the Ponceau-Tessner kernel. And once I verify that the space-like theory satisfies this equation, then I can just rotate all my momenta, multiply with this meromorphic function in front, simplify my expression, and voila, arrive at exactly at this equation. So this is why this meromorphic function that we got in front of these kernels was very important from the beginning to derive exactly this result. So this is what I'm saying here. The proof really starts from modular covariance of the space-like theory and uses the explicit relation between S and sigma, as well as the two non-trivial relations between the space-like and the time-like quantities. It turns out there is an interesting relation between the time-like DOCC and the space-like DOCC. They are related like so. And similarly for the two-point functions. So once I use all these ingredients, it is pretty straightforward to verify that this equation is true. And similarly, there is an analogous expression for crossing symmetry of scalar theories, in particular, an analog of that, which involves the fusion kernel. And here, it's not just one factor of OPE coefficients, but I have a product of two in the S and T channel. And indeed, one can go ahead and check with our expression for the kernels and also this expression that this equation is again satisfied depend upon the fact that the space-like theory is crossing symmetric. So was that clear? I may have tangled my words a little bit here, but feel free to ask questions. So I think there is a lesson to be learned here. So namely, the fact that we really started as having an input, the fact that the space-like theory is crossing symmetric, and then do all these manipulations and arrive at the fact that the time-like theory is crossing symmetric, really, I think has something to teach us about the bootstrap, in a sense that if we verify maybe that one theory is crossing symmetric for C greater than 25, then maybe doing some manipulations, one can verify that there is another theory at C less than 1. Of course, this is very ambitious. Again, we are working in terms of kinematical quantities. I haven't said anything about spectrum and solving the bootstrap equation and so on. But this is somehow the general lesson that we somehow want to derive from this exercise of Timelike Liouville theory, the proof of the crossing symmetry. So if I am to stretch this a little bit more, we know, for example, let's take C equals 1. We know that there is a plethora actually of known CFTs at C equals 1, have the compact free boson and some other models. So what about C equals 25? So in particular, like other than Liouville theory, we know so far nothing about C equals 25 Virasoro CFTs, just with Virasoro symmetry, and let's say non-holomorphic. But actually what we can do is we can compute an expression for the kernel at C equals 25. So given the relation at C equals 1, we can compute using our relations here, we can compute an expression for C equals 25. And it turns out in a paper by Yorgov, Lizovi, and Tiki in 2013, there was a very novel relation of the fusion kernel of generic C equals 1 theories with the Penleve 6 tau function. So these authors, after doing some hard work, they were able to relate the fusion kernel and the conformal blocks using some AGT relation and so forth with the connection coefficients of the so-called tau function of the Penleve 6 equation. And they were able to write down a very, very simple expression for the fusion kernel at C equals 1, which involves basically a product and ratios of the Barnes G function. So taking that expression, we can actually verify first in some limits that their expression is captured by our expression, except we have these complicated integrals here that we need to simplify. But indeed, in some regimes, we have been able to verify their expressions from our general expression here at C equals 1. Nevertheless, what they did is that they provide these simplified expressions. So all these complicated integrals that they are captured by our expression, they are somehow supposed to simplify in a way that we don't know how, to provide the connection coefficients of the tau function, basically. In any case, we can use the result to write down an expression for the C equals 25. And the fusion kernels at C equals 25, it will again be a simplified expression. In principle, it will be captured by the Ponceau-Tessner formula, which has all these integrals and so on. But with this connection that we have between the kernels, and using the fact that the C equals 1 kernel is very simplified by this work, we can write down a very simplified expression at C equals 25. And this is something that we're exploring currently. It looks like that the kernel at C equals 25 is another connection coefficient of this Penleve 6 tau function, except with rotated parameters. The parameters of the Penleve, they are rotated by Ni. So this is something that we are currently trying to understand. And what we hope for is maybe try to make a connection of these theories in great generality with these integrable hierarchies, and maybe eventually say something about the space of theories at C equals 25 and so on. But this is still in progress, I have to say. Okay, so I guess I'm about to conclude. So let me summarize and point out some future directions. So what we did is we studied the crossing kernels for Taurus one-point functions and sphere point functions in 2D CFTs. And what we did is basically we completed the study of Ponceau and Tessner by providing solutions on this missing regime. These are the expressions that we found. We saw that apart from the interest of having these expressions around, I think, we were able to find a novel application of this by analytically proving crossing symmetry of Timelike Liouville theory, which crucially relied on the fact that the space-like theory is cross-symmetric and modular covariant. And as far as we know, this was the first analytic proof of the fact that Timelike Liouville theory is cross-symmetric and modular covariant. The structure of this kernel seems to point out to an intricate relation between C and 26 minus C, which is yet to be understood, but our hope is that maybe we can initiate some kind of analytic conformal bootstrap program to explore maybe further these kind of relations, very ambitiously to the point where we might be able to say something about actual solution to the bootstrap. So some questions is, can we explore this further in some universal kinematic regimes of the bootstrap, let's say Lightning bootstrap, where all these kernels have been previously used? Can we say something about now those new kernels in these regimes? And again, very ambitiously, maybe we can use the reverse logic and let's say having the existence of the minimal models for all this, for this regime of C equals 1, can this teach us something about irrational C greater than 25 CFTs? Or maybe can we say something about, if we have holography in mind, can we say something about large positive central charge given some already known fact about large negative central charge? These are, of course, all far-fetched questions, but this is what we have in mind, what motivates us in this project. So with that, I would like to thank you for your attention.
Thank you so much, Ioannis, for a very nice talk. Do we have any questions for him now?
Can I ask you? So, Timelike Liouville theory is famously known to be related to, cosmologies. So, could you say that you could apply the Bootstrap program to understand cosmologies? In some sense, cosmological correlators, or?
Right. So, I'm not sure how this expression for the kernel can be applied to those kind of settings. So there are these papers by Beatrix Muhlmann and Teresa Bautista and Ioannis, where they have 2D gravity models coupled to conformal matter with positive cosmological constant, and they take the matter central charge to infinity in order to find some semi-classical saddle, which forces the Liouville central charge to be largely negative from the conformal anomaly cancellation. I still have difficulty to see how these expressions for the kernel, at least we don't see yet, will be relevant for this kind of problems, where you are basically interested in computing correlation functions and then integrate over the moduli, let's say. Yeah, I don't have a clear answer.
Okay, thanks.
Any other question?
So, Ioannis, how much of your work, does any part of this work rely on this old story about the analytic continuation of Liouville theory, where they studied this DOZZ formula and tried to understand its continuation?
Right, that's a very good point. Actually, we were motivated originally by that. So the space-like DOZZ formula satisfies some shift relations. And then in this paper by Zamolodchikov in 2005, if I'm not mistaken, where he was able to write down the Timelike structure constants, he was basically arguing for the fact that the space-like DOZZ, you cannot analytically continue the central charge, but you can analytically continue the shift relation that the space-like DOZZ satisfies. So the proper thing to do is not take the space-like DOZZ and try to analytically continue to its time-like counterpart, but start from the shift relations, analytically continue them, and then ask for a solution. So, and indeed, what he showed is that there is a time-like structure constant which has nothing to do with the space-like DOZZ. Actually, they are related in a funny way, like so. So this is the space-like DOZZ, except take it to be valid at IB and rotate all the momenta. The inverse of that will give you the time-like DOZZ. So motivated by that, we said, okay, we should not try to understand these kernels just by analytically continue them, but let's go back to the difference equations that these things are satisfying, the pentagon identities, and ask if there is a solution, let analytically continue B, and then ask if there is a solution. And these are the solutions that we obtained.
Thanks.
Okay, if there are no more questions, let's thank Ioannis one more time.
Thank you very much for having me.
Thanks.
Thank
That was a really nice summary at the start and nice
Thank
results.
you. Thank you. Thank you.